what happens as you do these numbers here? Let's use a different example here. If you have this, I don't know if you remember when you're in elementary school and they had you write numbers like this, 3,275. They had you write it as 3,000s, right? Like 3 times 1,000 plus 2 times 100 plus 7 times 10. I'm sure you all remember that, right? Plus 5 times 1. Like right after you learned place value, you wrote it in kind of that expanded notation.
I love that.
You factored that when you were in grade 2? Is that what you're saying? What you were writing, even though you didn't know exponents then, was you were saying it's 3 times 10 to the third plus 2 times 10 to the second. I mean, that's what this means, right? Plus 7 times 10 to the first plus 5 times, I mean, you don't have to do 10 to the 0, right? But you could. This first digit represents the thousands, right? If you make this x now, all you're doing is you're saying I'm not working in base 10, I'm working in base who knows what, right? I'm making this number bigger now. So you have a polynomial like that. Which one of those is the most important term if you're talking about how much money that was, right? If you're looking at this, which one matters the most if it's an amount of money? This one, right? This is the dominant term, right? That's the one you care about changing if it's your bank balance. If this one changes, it's not such a big deal, right? If this was an investment you had in something and this digit changes, that's not such a big deal. But if this one changes, that's a big deal. That's the dominant term. And as you work in different bases, right? If we change this now to be, we're basically changing the base we're counting in as you change x there. If you make that a larger and larger number, it just exaggerates what difference that makes, right? If we're talking about this is, if x is 100 now, right? 100 to the third is now, it's like 3 millions, but this 100 squared is only 10,000. 10,000 is less significant out of a million than 100 is out of 1,000, right? 100 is a tenth of 1,000. 10,000 is a hundredth of that, right? This is a tenth. This is a hundredth, right? The larger you make x, the less this matters to that. The larger you make x here, the less these terms matter. Think about, we're talking about money in the thousands. Think about money Bill Gates has. He has a lot of digits, right? I don't know what he has. Probably lost a lot last year. Probably lost 30 billion or something like that. Well, no, that's a biggie to him, but let's pretend it was, I'm going to put some random numbers here, but this is totally random, but 31,275,463,219. Okay? If you had to write that out in expanded notation, and you're a grade 2 or whatever, that is depressing, right? But think about this term is the most important one, right? This term is the least important one. And that's when we're working base 10. If you increase that, right? If you increase the x value, it just exaggerates that difference. This is, to him already, this is pretty meaningless, right? That's so insignificant compared to that. Right? Think about how that compares to you. So you don't have in the billions, right? So even he has some cents here. 49 cents, right? If you move this decimal to what is more reasonable for us, what might you have saved in the bank? Or what? 31 cents. $31? Even if you have, let's say you have 3,000, okay, and we put it there. Look at what this, or even this is. That would be the equivalent of, like, him, let's say he loses this, he has $9 in his pocket, it falls out, and he doesn't even have to bother picking it up because it's so insignificant to how much money he has, right? I know he would. I'm saying that's the equivalent of you having not. Look at the decimal place relative to how much he has, or relative to how much you have. That would be the same as if. Look how many decimal places this is. If we looked at that as how much you had, 3,127.54 cents. This would be tenths of cents, hundredths of cents, thousands, 10,000s, 100,000s of cents. $9 out of 31 billion is like 9. What did I say? hundred thousandths, 900 thousandths of a cent. I know you can't carry that around in your pocket, but if you drop a penny and it rolls over there, I'm pretty sure you're not even that running to pick it up, right? People leave a penny, take a penny in all the stores now, you know.
I take mostly.
You take mostly. Not good. Anyways, as you get bigger and bigger values, the smaller terms become less significant, and this is the dominant term. So as you make x approach infinity, they're identical, because these are so insignificant. It's hard to comprehend letting x approach infinity, but the leading term, those behave the same way. That's what an end behavior model is. If you want to kind of show that something's an end behavior model, you have to show that this is true. So if it says show that this is a right end behavior model for this function, you need to show what it says up here. And if you want to show that this is a left end behavior model, you have to show what it is down here. We'll talk about this together in a few minutes, but I want you to try it first. Start with a statement like this where you're filling it in, and then try and simplify it algebraically and make an argument for why it works. The right end behavior model is going to be easier here algebraically than the left end behavior model. Can you try that for yourself or with a partner right now? I don't know why that's so exciting, but okay, you learned something. You learned how to make a ball go across your calculator screen.
What's the ball do?
The ball does nothing. It just, if you want a ball there, I don't know.
I like the ball.
Okay, let's draw this back together here.
4 minutes.
These two functions are behaving more and more the same as you go to the right. The limit of their ratio, since the values, if you looked at the table, okay, again, if you set up the table and looked at it, just like before, if you start to scroll down here, well, now I've started at a point where they're, what have I got here? Oh, it's so insignificant, actually, that let's start at the beginning here. This is actually good to see that the values are, this one will more quickly let you see that the values are becoming the same, because as soon as you're going e to the power of negative x, that changes pretty quickly. This is going to be, I mean, it only displays 11, but it's 11.00. These are quickly becoming almost identical here, and pretty soon you run out of you get past the power of this calculator, and it'll show them as the same, the power or lack thereof. If you want to show this analytically, let's do this quickly here. The limit as, what do we have to show here? Limit as x approaches infinity. If we want to show that this is a right end behavior model, you have to show the limit as x approaches infinity of f of x over g of x equals 1. Or in other words, limit as x approaches infinity of, what do we have here? X plus e to the negative x over x equals 1. It's kind of like a proof that you would have done in Ca12, trig identities. You know, you can start with that statement and show that it's, I mean, just keep working down each side and showing whether it's true or not. If you have a function or a ratio like that, you can split it up. X over x plus e to the negative x over x. Now, you have to do some thinking here, right? X over x, what's that the same as? 1, right? So this is 1. And e to the negative x over x, you have to remember what negative powers are. It's the reciprocal of that, right? E to the negative x is like this is on the bottom of the fraction. It's like the reciprocal, right? So this is the same as 1 over e to the x times x, right? 1 over x times e to the x. Are we okay with that step there? All right. Now, here's where we have to do some thinking. This first part is easy, right? This is 1 to actually evaluate the limit. But this is the part where you have to think here. If you let x approach infinity, what you're thinking is, what are you thinking? Because you're not happy, you mean? Or infinity, 1 over infinity times e to the infinity. Well, 1 over, okay, think about e to the infinity, what's that? Infinity, right? You can't get any bigger than infinity, so e to the power of infinity is infinity. And then you have, infinity times infinity, what's that? No, okay. 1 over infinity. 1 over infinity is like 0. This is 1. I can actually go to about 10 minutes and 20 seconds or something like that.
1 minute.